Okay, let's dive into this. Have you ever stopped to wonder what actually holds up our digital world? I mean, we're completely obsessed with flashing apps, stunning graphics, and cloud-based AI, right? But beneath all of that hype lies this invisible, virtually indestructible architecture. And that is the C programming language.
To really understand the stakes here, just think about the screen right in front of you. The operating system running this very explainer, whether you're on Windows, macOS, or Linux, is basically built on C. From your computer's device drivers to massive database systems and embedded hardware, C is literally the invisible engine that keeps the whole digital world spinning.
So here's our blueprint for today. First, we'll look at the bedrock of modern computing, then the anatomy of a C program, next, data types and variables, after that, logic, loops, and functions, and finally, why learn C today?
All right, let's start with Section 1, the bedrock of modern computing.
So C was developed way back in 1972 by Dennis Ritchie at Bell Labs. Now, in the incredibly fast-paced world of tech, anything from the 1970s usually belongs in a museum, right? But C is the ultimate exception to that rule. It actually became the DNA for major languages like C++, Java, and C#. And honestly, it hasn't retired at all. It's still actively powering modern operating systems, embedded systems, and even the compilers that translate other programming languages.
So the crucial point is that its survival really comes down to its unique positioning. C is widely known as a middle-level language. What that means is it perfectly bridges the gap between human-readable high-level code and the raw, low-level machine hardware. It essentially gives you direct access to memory and system resources without actually forcing you to speak entirely in ones and zeros. Because of that awesome middle-level position, C brings some truly indestructible building materials to the table. We're talking incredibly fast execution and high portability, meaning code written for one platform is going to run smoothly on another. It promotes structured programming through these really rich built-in libraries, and perhaps most famously, it gives you direct, unadulterated access to memory management. It's an absolute powerhouse.
Moving right along to Section 2, Anatomy of a C Program.
Now, every C program follows a pretty strict logic. If we look at a classic Hello World script, we always start by including our standard input and output library. Then we open the main function. You can think of this as the front door where the execution actually kicks off. Inside that room, printf displays our desired output, and finally, return 0 turns out the lights. That just signals to the computer that the whole program executed successfully. Pretty straightforward, right?
And this brilliantly illustrates how you can scale that up to get real work done. Take a look at this basic addition program. We define our variables, feed it an input of 10 and a second input of 20, and then the core logic processes them to build a functional output, which gives us a sum of 30. Basically, your raw materials go in, and a finished product comes out.
Okay, next up is Section 3, data types and variables.
To process anything at all, C needs designated memory allocation. You can kind of think of variables as the internal wiring and precise storage containers for our house. When you declare something like int age equals 25, you aren't just writing a word. You are actually reserving a very specific block of the computer's memory to hold that exact piece of data. So, whenever the program needs that value, it points straight to that specific box.
Now, what's really interesting about this slide is seeing how brutally strict C is about organizing these containers. A box has to perfectly match its contents. An int is specifically for whole numbers. A float handles your everyday decimals. A char stores single characters, and a double secures those highly precise large decimal values. This strict, static typing might sound rigid, but it's exactly what makes C so dangerously fast and efficient.
Let's move on to Section 4, Logic, Loops, and Functions.
So execution really relies on dynamic routing. Through standard conditional statements like the if and if-else commands, C evaluates memory states in real time. For example, it might check if an age variable is greater than or equal to 18. Based on that single check, it instantly forks the execution path. It either outputs adult or minor, routing that data dynamically without any hesitation. Of course, real automation requires loops. Instead of painstakingly writing out sequential code by hand, C utilizes structures like the for loop to rapidly cycle through memory blocks or execute repetitive logic. It acts just like a high-speed assembly line in a factory, drastically optimizing both the size of your code and how fast it runs. Now, when you're dealing with massive data sets, creating individual variables gets messy.
That's where arrays come in. C uses them to allocate one continuous block of memory for values of the exact same type. Let's say you have a bunch of test scores. An array conveniently turns those 5 scattered data points into one highly organized indexable sequence. It's a real lifesaver for organization.
All right, this brings us to what is widely considered C's ultimate superpower, pointers. Now this can be a tricky concept, but stick with me. Rather than holding a standard data value, a pointer holds the literal memory address of where that data actually lives. Think of it as the exact street address of the hardware memory block. This direct, unfiltered ability to manipulate memory is the real secret behind C's blistering speed and power.
To maximize efficiency even further, C utilizes functions. These basically divide massive programs into modular, reusable blocks, like prefabricated rooms you can just drop into your building. Instead of rewriting complex logic over and over, like a routine to print a welcome message, you just package it into a function, let's call it greet, and call it whenever you need it. It keeps your codebase super lean and highly maintainable.
Finally, let's look at Section 5. Why learn C today?
Let's move to our final points and see how this all builds into something incredibly valuable today. The return on investment for learning C is just staggering. It literally forces you to understand manual memory management, which gives you a ridiculously deep understanding of bare metal computing. It remains the absolute undisputed king of embedded systems. And because it's the foundational syntax for so much of modern coding, it essentially hands you the master key to easily conquer languages like Java, C++, and C#. Oh, and it's absolutely crucial for passing those rigorous programming interviews too.
So, as you can see, C isn't just some relic of computing history. It is the living, breathing architecture of our modern digital reality. By mastering its memory allocation, its loops, and those powerful pointers, you aren't just learning to write code. You are literally learning to command the machine itself. So the question isn't whether you should learn C. The real question is, what are you going to build once you possess the master key?